Good afternoon, everyone, and welcome to today's Resilience of Autonomous Systems seminar. I'm Radu Calinescu. I'm a professor of computer science at the University of York, and I'm the principal investigator on the Trustworthy Autonomous Systems node in Resilience. And I'm really delighted to welcome our speaker today, Professor Gopal Ramchurn, a professor of artificial intelligence at the University of Southampton. He is also a Turing Fellow and Fellow of the Institution of Engineering and Technology. And he's the director of the UTRI Trustworthy Autonomous Systems Hub and co-director of the Shell Southampton Center for Maritime Futures. He is also co-CEO of Empathy Limited, which is an AI startup working on decentralized green hydrogen technologies. Gopal's research is about the design of responsible artificial intelligence for socio-technical applications. This includes energy systems and disaster management. And his research work in this area has won multiple Best Paper awards. He is also a winner of the AXA Research Fund Award for work on responsible AI. He has pioneered the development of AI-based disaster response systems using multi-AV systems, AI-driven large-scale battery management for smart grids, and an AI bot that outperformed over 5 million human players in the English Premier League fantasy football tournament. He has papers cited over 9,000 times, according to Google Scholar, and he is originally from Mauritius and is interested in promoting applications of AI for environmental sustainability. So without delay, would you like to start the presentation, Gopal?
Sure. Thanks, Radu. And thanks again for inviting me to give this talk. I think it's the first talk I get to give to members of this Trustworthy Autonomous Systems Network. Yeah, so very grateful for all of your time. I hope I get some feedback on this talk because I'm hoping to give this talk to a number of venues to present some of our views on the TAS program as well. So I'm going to cover some technical elements as well as some broader issues that the TAS program is trying to address. So I'll just share my slides. Hopefully that will work. This first. Is that okay, Radu?
That is absolutely fine.
Right. So my talk is going to be about trustworthy human AI partnerships. It's a paradigm, I think, that helps us think about the right questions when it comes to addressing notions of trust. And for most of us, I think in this seminar, it's very clear to us, that autonomous systems, AI-based systems, machine learning systems are all around us in its various forms, whether it's in autonomous vehicles taking us around cities, or facial recognition systems that are used by supermarkets or on our phones, predictive policing using our data, historical data about crimes and human behavior to predict where to place police cars or to catch criminals, and warehouse robots, where you have swarms of robots carrying boxes around warehouses in a coordinated fashion to optimize throughput through a warehouse and delivery times. So they are everywhere, and right now we're starting to grapple with some of these issues, these ethical, technical, legal, regulatory issues, challenges. And we're sort of surprised. We tend to be surprised that they're all coming up now. We tend to be surprised that, oh, someone might be collecting data they're not supposed to, or these robots might fail and things might go wrong in this warehouse, and the whole warehouse might catch fire, as it did with the Ocado warehouse. Or the policing methods might be an overkill for some of the crimes that we're talking about, or biased and reinforce biases that exist in society. Or autonomous vehicles might lead to more accidents because we can't control the handover process. We can't be sure that humans will be able to manage unforeseen events. So why do these issues arise in the first place? Why are we surprised, and could we not anticipate them? And that's the thing that really worries me, is that we tend to build these systems, change the world, hoping to change the world, and then things break, and then we're surprised that they break. And maybe many of these issues we could have thought of before they were actually deployed. And none of these technologies were sort of built with the intention of causing harm, right? But right now we are worried about these questions which are to do with what machines do to us. We tend to have this adversarial relationship with machines, with AI-based systems. So we start thinking about how do we build them so that they're reliable in extreme environments, or can we make sure that they don't reinforce these biases in the data they train on? Or we try to come up with good models of risk for these adaptive systems, and help insurers cope with these functionalities that change over time. Or we try to think of different ways of doing the handing over between the vehicle and the driver in these settings where the vehicle may need to navigate a very dynamic and uncertain environment. So this is all, I think, reacting to this question of what machines do to us. And the question is really, who is responsible for the safety and reliability of this system? Are we clear about that? What is the system we're talking about? In many cases, it's not clear what is the system. And I hope I can give some insights on how I think we should think about systems of humans and machines. And I think questions of trust are more about what machines do with us rather than what machines do to us. And if you start thinking about research based on this paradigm of human-machine partnerships, human-AI partnerships, the questions will change, and the answers will be different, both in terms of the research that we do and in terms of how we implement them in society. So let's ask different kinds of questions. So that's what I suggest, in terms of changing the focus. To point to sort of to machines, to context where machines do things with us. For example, will my children be safe in an autonomous car on their way to school? That question changes the way you think about the design of the car, the certification of the AI system that goes into this car, the insurance that's associated with this car, the environments within which these vehicles are allowed to operate, and the comfort you give to the parent in the way the safety measures are designed in the system in this vehicle, how these promoted to the user, and then how many users here. You have the passengers and you have the parents. Will my grandma be safe in an autonomous smart home heating system, right? So if my home is heating itself and I leave the house for a month, what will happen? Do I feel that the home will look after my grandmother? Well, will my customers buy an autonomous car without a steering wheel? Can we really transition to a world where companies, manufacturers will be comfortable with selling a car without a steering wheel? Will that make any economic sense to them? Are the current laws clear about who is responsible? If a swarm of autonomous drones crash while delivering a package in windy weather, who's responsible at that point? If the swarm is making decisions on its own, or if there may be some human operators in charge of this swarm, it's not clear potentially who's responsible. And of course, you have the traditional issues around, whether the operator of a robot will eventually be taken over by taken out of the system by the robot itself. So if you're training a robot to do something, will the user be comfortable in training it correctly? And what should government policy be to prevent AI-induced social exclusion? That's something I'm quite passionate about, is to understand where automated decision-making may have an influence on social exclusion. So let's maybe dig a bit more into some of these questions. So typical way of addressing this question, the first question was, will my children be safe in an autonomous car on their way to school? And people will tend to focus on the accident rates, right? And say, oh, okay, autonomous vehicles have an accident rate of 0.1%. So you think then, as a parent, is that enough to convince me to put my children in that car? Or will I worry about the airbags? Will I worry about the messages that the vehicle gives to the occupants when something goes wrong or something is about to go wrong? Do I have a way of monitoring the occupants of the vehicle? Do I have a way of tracking the vehicle as it's going around? So however sophisticated this vehicle is, there's a relationship that forms between the parents and the occupants and the operators of the vehicle, the monitoring system of that vehicle. Do I trust the communication system? For example, if it's navigating in an area where there's poor mobile comms, right? So there are other questions that arise, and let's look at another one. So can I leave grandma with a smart care system for a weekend or for a month? So on the right-hand side, you have one of these smart thermostat systems, and on the left, you have this smart care robot that we're all trying to build in, some of us in the task program. So so this robot is giving a syringe to this lady, and with expectation that maybe she understands how to use this. Or you may have robots that give pills to the patient, and or you may have just boxes that beep to remind the occupant that they need to take their pills. And you have similarly, home heating systems that may heat the individual rooms, or may turn on and off the lights. So if they're smart home systems, for example. And you as a carer for that person need to decide whether this system can take over your role. Can they decide on your behalf? And then can they react to various behaviors of that occupant? So if grandma decides, and maybe grandma is suffering from dementia and forgets that she's already taken her pills and keeps pressing the button to get more pills, will the system say no? And if the system says no, does she take the box and try to open it up herself? And then can the system react to that? Can inform you? Or if it's a home heating system and grandma is feeling cold and decides to turn the heating up and turns it up too much, and the house gets really dry, how do you react to that? Is that serving the sort of the objective of the system? And there will be lots of feedback loops in these systems that will potentially end up with the users rejecting the system. As I found out myself, I've had one of these smart home heating systems, and it is very good when you're a single occupant in a home and you've configured the system to react to your geolocation. So if I leave the house, the heating goes down and saves me money, but it actually turns off the heating even though my kids and my wife are at home, and that's not a good system. And the app, however cleverly designed, is not usable, is not very friendly to my kids or to my wife, and therefore they may not be able to react to such changes in the home's behavior. And in the end, we end up rejecting the system. So there are lots of good applications like this that will end up getting rejected because we've not thought ahead of time how to design them properly. This is another example of asking the right question about autonomous vehicles. We tend to think of autonomous vehicles as being a very sort of, I think, first world problem. We tend to think about handover problems, accident rates, etc. But do we really ask the question about who are the most likely to benefit from autonomous vehicles? Are these the elderly? Are these those with childcare duties? Then how do we design autonomous vehicles and the interface with these autonomous vehicles? Should the occupants of these vehicles be of a certain type? Or are we designing them for the first adopters? Those who have lots of money to spend and really want the latest tech. So really thinking about the social benefit of the system to the wider society before we go out and design the system. So thinking about who will benefit most and how do we pitch these systems to them. And this is a big question that industry would like to have answered. Going a bit more technical on the sort of the robotic side, for example, how do we manage a swarm of drones? Who is responsible at any time, as I mentioned earlier? And in many cases, we tend to blame the system. We tend to say, oh, the system is poorly designed, the interface is poorly designed, or the sensors fail, etc., etc. But if you look at the various drone crash reports, and the link is down at the bottom of this slide, you can read all the reports from at least some of the reports from the Watchkeeper program. So Watchkeeper is a drone program. So there's 7 of them that were manufactured, and all of them crashed mainly because of human failure or failures of the team. And to fly one of these required a large team, potentially more than 10 people, some looking at the sensors, some looking at the navigation, and there were mistakes made by the team rather than by the system itself. The system did have some issues. There was sensor failures, but in the end, someone pressed the wrong button, or someone said something during a meeting, and the wrong decision was made, and they crashed. And they crashed quite close to human populations. So,
tools in order to work, but also changing how we change. And this is something that is interesting because we are under a paradigm that
can't hear you very well. Okay, we had some noise on the call.
I think someone was not muted. Gopal, sorry about that.
Right. So I just picked out one of the accident reports here. So where the captain during the interview reported feeling under pressure to land, to stay within the crew duty period. So they have these crew duty periods when they have to finish part of their mission, and they feel under stress to complete the mission, and they end up making the wrong call at the time. So when we design this system, do we really think about the humans involved, the human teams involved, how they will interact with this system, what should we build within the system to react to their failures? The last question I had was, how do we regulate AI? We hear a lot of talk about the EU AI Act. The UK government recently published its pioneering standard for algorithmic transparency. You can go and download it and see what you need to report when you use data in algorithms. The NHSX is leading the way with some of the regulatory bodies in the healthcare sector to help inform regulation of AI-based medical devices or recommended systems. But can we really define risks for adaptive systems, AI-based systems of all types in one go? And I don't think we can. I think it's very, very hard to pin down, characteristics of AI systems that are common across all AI systems in all sectors. I think we need to think about the context within which they are deployed and then define risks accordingly. And to pick up what John McCarthy said, as soon as it works, no one calls it AI anymore. So can we really legislate for something that we all define differently, or disappears as soon as it works? So we need to think more broadly about AI and AI-based systems in general, and how in the context within which they'll be deployed. So I offer, recently we wrote this paper on HumanAI Partnerships, on trustworthy HumanAI Partnerships, because I think we need a different way of looking at AI-based systems, and not just AI systems as solipsistic machines that are just sitting there on their own and do things to us. They actually do things with us. So thinking about HumanAI partnerships instead of just of autonomous systems on their own tend to sort of capture these systems as social technical systems composed of humans and machines, where both machines and humans may be in charge at different points in time. So machines and humans influence each other. Machines may take control of the system for some period of time, and humans may take control of systems at other periods of time and dictate what the machines do. And looking at humans and machines as collaborators, so cooperating, coordinating in very dynamic and very dynamic environments, and coordinating in different ways, potentially different sort of hierarchies, different modes of working, and potentially also competing with each other as they do react to incentives placed to them. In these human AI partnerships, we also expect many feedback loops to exist. And these feedback loops may reinforce beliefs and influence that long-term decision-making. And human AI partnerships are expected, or hopefully will be designed to be ethical and safe. And I'll try and cover some of that in this talk. And I'll give some examples here. I mean, the film industry has been very good at shaping our understandings of human AI partnerships. I try to refrain from putting killer robots on my slides, because I think they're much better examples of human AI partnerships, and there are some good and bad examples. And you have those where the human needs the machine and the machine needs the human, as in Star Wars with R2-D2, or the Knight Rider with the car that comes to the rescue of the David Hasselhoff here, in many situations, and has a mind of its own and can work with many more humans in one go. Also in this picture, by the way, you see Michael Knight talking to his Apple Watch, or what was the Apple Watch at the time. But yeah, many of these systems actually inspired me to go into computer science, because I really like the idea of humans and machines working together. There are also bad examples or examples of bad behaviors or poorly designed human AI partnerships, or examples where you can see the machine deviating from its original design objectives. The most recent one is the Fear Index, which is a series running on TV at the moment. And in this case, a human designs this AI to exploit fear in the markets, and then the machine becomes so clever as to manipulate humans and for its own benefit, and its benefit being defined by its own defined objective function. And these are some sort of raise interesting questions around how should we engineer these systems, how should we design them, but also our relationship with them. So how do we monitor them? How do we monitor the humans that are manipulated by them, or how do humans manipulate them for their own benefit? So there are three aspects or challenges I see, and there may be many more, but the three main challenges around managing human AI partnerships. These sort of tend to focus around managing data, around the design of human AI partnerships, and incentives, incentive engineering for human AI partnerships. And we need to deal with all of these if we are going to make them trustworthy. I'm going to try and explain what I mean by this, and then give you two examples of how we move from a pure AI-focused system design to one looking at human AI partnership design. So when we look at human AI partnerships, particularly when there's data involved, where you have continual learning systems that learn from human input, and we have many examples, as I mentioned earlier. You have machine learning systems that learn from historical crimes, for example, or historical recruitment, so in job applications, and then provide the recommendations to the human operators. And the humans react to that and decide on a particular course of action. So they may decide to police a certain area of the city. And again, as I said before, they reinforce certain biases. I put a picture of the Netflix screen here where it shows you, if you're not sure what to watch, let me play something to you. And that feature in Netflix learns from your historical viewings and picks stuff that looks like what you've seen before. Basically reinforcing your preferences, trying to look for things that align with your preferences, or trying to reinforce a certain metric which they may influence, In Instagram, for example, there was a really interesting documentary on Instagram where they define the metric as meaningful social interactions. And meaningful social interactions is defined mathematically by them, and no one knows exactly how that works. But presumably something to engage you to view more ads, right? But over time, you are reinforcing these beliefs, you're reinforcing those preferences, and these will lead you potentially to bad outcomes. So in large systems, when you have lots of independent actors learning from each other's behavior, you can imagine there will be lots of oscillations in those systems, lots of oscillating beliefs, and potentially a system which takes away human autonomy. So our ability to learn new things, our ability to enrich our knowledge, our ability to monitor and control those systems. So we need to worry about breaking those positive feedback loops, as I call them, in this setup. We also have the issue of tracking data and decisions made on this data. For example, the example below on the right-hand side looks at a human UAV team. So you have multiple humans, you have multiple drones collecting data, you have humans on the ground collecting data in a hazardous environment. Machines may be working intelligently amongst themselves to decide on where to collect data, maybe informing human decisions on the ground, and they're doing this at machine speed. And humans are reacting to these machines, giving them information and generating their own data on top. At some point, things may go wrong. And therefore, someone needs to react and decide why it has gone wrong and what are the remedial actions to take. So we need to be able to trace back to the source of that decision, understand what caused that decision to be wrong. And in those cases where these systems are really, really large and autonomous systems are making decisions at machine speed, without a trace of these decisions, it's very hard to understand who's responsible for what, to understand what was the cause of a specific outcome. So this will become increasingly difficult as you have multiple machines talking to other machines and many humans across large organizations. And which is why I tend to think we need to have a way of tracking the provenance of these decisions. And as you expect, tracking provenance in such large systems becomes intractable. And therefore, you have to have another approach to doing this. And you may need to summarize, aggregate these provenance traces, may need to be able to detect or classify decisions in these large systems and try and identify causal relationships between the various actors and data points, data sources in these systems. So that's a really, really tricky one. I'll give you an example later of how we might solve that. The next sort of challenge is around design. And in many cases, many problems at the moment, we tend to focus on explainability, understanding machines or black boxes. And black box here tend to be those machine learning, deep learning systems that we try to make more interpretable, more explainable. But I tend to think of larger systems, of systems of multiple machines, as I showed in the previous example, of drones, of multiple autonomous vehicles, of algorithms making decisions for us in large systems. And these are equally black boxes to us. We can't really understand or explain their behavior. So how do we design our interactions with them? How do we design teams to work with them? How do we design interactions between us and our personal assistants, for example, our virtual personal assistants? So how do we design interaction between our personal assistants and other people's personal assistants? To give you an example of what I mean by that and the complexity of designing this is an example I took from a paper we wrote back in 2016, where we built a system for disaster response. And here you have these loops, decision-making loops. You have in disasters, you have to collect lots of data. You have to send people out or drones out to gather data from the ground. You have to classify this data. You have to make sense of it and decide on what targets you're going to choose to focus on. And then you need to identify casualties. You need to identify tasks to do in the environment, and then allocate your emergency responders to these tasks. Structuring these sorts of teams of humans and machines is a really big challenge. How should you combine human and machine intelligence, for example, in classifying reports from the crowd on the ground? Should you let the humans classify everything and then get the machine to aggregate all that information and summarize it? Or should you let the machine decide on who should classify what? Or should you have the machines filter that information before it goes to the human? And then how do you allocate drones, for example, to carry out a survey of the environment? How should you structure the team? Should you have humans, multiple humans looking at camera feeds, sensor feeds? Or should you have the drones automatically running their own computer vision algorithms and sending out their own insights? Would you trust that? How do you scale such systems? It becomes really, really tricky. And that's where we, as you can see, the team that we brought together to build one of these systems is quite large. It is not just doable by one engineer building a solution. It is not just a pure engineering challenge. It does require multidisciplinary teams to build. It does require a participatory design approach. And in some cases, if you would like to verify how these systems would operate in reality, you may need to construct simulations of them, because recreating, for example, a disaster is not something you can do on the fly, right? So you might want to create agent-based simulations of those, and I think that's how you might be able to explain their behaviors. You might be able to explain or interpret their decisions in a very complex setting. So building the simulations, designing them in a participatory way and iteratively, taking a user-centered approach. The third and final set of challenges for these human AI partnerships, for me, lie in incentive engineering. And I mentioned earlier the challenge of modeling what's going to happen when we delegate decisions to our agents, to our personal assistants, for example. The examples I have on the right-hand side, for example, are to do with an electric vehicle. And if you leave an electric vehicle to charge by itself, it may charge for 8 hours straight, and in the future it may decide that it will react to prices on the grid. So when should it charge? How much should it charge will depend on the price on the grid, but also depending on your personal preferences. So you may need to charge your car very quickly, within 2 hours, but the vehicle might need to trade that off against the price of electricity. So can the vehicle then model your preferences? Will it be able to do that without sharing your data with your preferences with the utility? And can we avoid burdening you with too many questions as to when you want your car ready? Can we learn that time to leave, for example? So there are challenges around preference modeling when we start building these human AI partnerships. We need to worry about not invading users' privacy, but also not bothering them too much, so that they become seamlessly integrated in our daily lives. The second element of this incentive engineering problem is the idea of incentive design. And typically, we design systems that will incentivize good behavior to maximize social welfare, through truthful reporting. So people report truthfully when, for example, they would like their car charged, or where they would like to meet. And as the example on the right-hand side at the bottom shows, can we agree on a price for property, or can we agree on a time for a meeting? And would we reveal our preferences truthfully if this were submitted to a system? And the challenge there again is to do with people being able to do that while preserving privacy, but be able to do that in a very dynamic environment where the algorithms need to learn our preferences or react to our changing needs as we engage in different kinds of interactions. So again, here we need to use fundamental techniques like mechanism design, game theory, interactive machine learning systems to solve these problems. I have a few more slides to go. This is just to give you an example of how we move from a pure AI-focused system to a human AI partnership based design. So this is an example from disaster response again, where you have humans, what we call the silver team, the tactical team, deploying a team on the ground, which we call the bronze team. And we design an agent to optimize the deployment of that bronze team. So the bronze team may be made up of ambulances, fire brigades, police, so search and rescue teams. And here, the first version of this algorithm looked at modeling this using a multi-agent Markov decision process, where the algorithm tried to maximize the performance of the system of the teams by allocating tasks to individual members of the team. And what the algorithm would spit out in a simulation, so we simulated the system, and the algorithm was shown to work really well. We published that paper separately, and we tried to implement it in this real world system. So deploying it in the real world with this dashboard, which would give to the operator, with the algorithms running on the apps, on the mobile phone apps. And we also tested this with emergency responders. And the algorithm would basically suggest the best allocation of tasks to the members on the ground. And the people on the ground would be allowed to say, no, I don't want to go and do this task, or I want to work with team Y, which is doing this, rather than team X doing that, right? So they had a choice as to where they could go and what they thought they would be best suited for. And that system worked, but it failed in a number of ways. So first, it allowed users to reject tasks. So it let them indicate which team they wanted to work with. And that caused the algorithm to keep spitting out new tasks for them, and eventually converge many times on the worst outcome, or the closest task, or tasks that they could do on their own. We tried to stop that as well, but it tend to converge to a local minimum, and that's not good for the system. And that happened mainly because we could not account for human preferences. It was basically the algorithm, the objective function you see here, the value of the various states in this system didn't account for human preferences to work with certain teams. In version 2 of the algorithm, we looked at computing the best teams to allocate tasks to. So we had the idea of capturing the rejection probability within the algorithmic framework. So within what we call the KRMMDP. So it is a framework that allows the individual agents to reject tasks. So the underlined bits here show you the different branches of the decision tree that would lead to either rejection or the acceptance of the task, and therefore the value of future allocations to the individual, to the team at that point in time. So that by modeling that and then changing the interface, where we allowed the headquarters to review that suggestion from the algorithm and then offer that to the humans on the ground, we're able to show that it improved the performance of the system. So basically, the algorithm was optimizing for the creation of the best teams, accounting for trying to learn which teams individual players would like to work with. And then we changed the interactional arrangement between the humans and the algorithm. So the human mediator helped explain the decision of the algorithms to the humans on the ground, and helped the humans on the ground explain their decisions to the algorithm. So there was a two-way conversation between the humans and the algorithm in this case, which allowed us to solve that problem with the objective function. And it was trialed and successfully trialed in a mixed reality game, which we called Atomic Orchid at the time. A second example, just to conclude on that front, looked at demand response in power grids. So, not sure if you're familiar with this problem, but as we have limited energy resources in many developing countries in particular, we tend to try and reduce our energy consumption. In some cases, it results in shedding loads from the grid. We're literally turning off parts of the grid. And initially, we designed an algorithm to optimize which home would turn off their consumption or would reduce the consumption. And that led, obviously, to the homes with the highest energy consumption to turn off less often. So the utility of the system was based on how much consumption you were able to satisfy at any point in time. So you could cut out many more homes of the lowest consuming homes in version 1 of the algorithm. But then looking at what we wanted to achieve as a system, we wanted to make sure that the distribution of energy is fair across the system. We turned to a centralized decision-making process, looking at people's reaction to disconnections, for example, from the system. So, for example, looking at envy freeness as a metric, or egalitarian measures, and it results in very, very different outcomes when you try and meet these sorts of objectives. For example, on the right-hand side, we designed the algorithm to react, various algorithms to react to maximize the amount of time people had in terms of connecting to the grid, or the amount of energy they could consume from the grid. And we designed various algorithms, for example, algorithms that would minimize differences in disconnections or minimize differences in comfort. And we had a way of modeling comfort of homes as well. So that shows you that, if you think of the problem as being a comfort problem or a fairness problem in terms of disconnections, it leads you to very, very different outcomes from thinking of a purely utilitarian perspective, that is maximizing the sum of the individual homes' utility functions, or even just forgetting about comfort and in terms of or disconnections being and its huge inconvenience to these homes. So key takeaways for me from these slides on human AI partnerships, I think we should be focusing on what machines do with us rather than what machines do to us. We should be more reflective. We should try and anticipate these unintended consequences to individual society and industry, and rethink as engineers, as AI engineers at least, and work with experts from other disciplines to iterate the design of these human AI partnerships, and learn from the end users' perspectives what are the key concerns we should be addressing. So a number of challenges I mentioned arise from within the paradigm of human AI partnerships: feedback loops, data and decisions in very complex human AI partnerships, human AI partnership design, and making these systems verifiable and explainable when they can be quite complex and large. And finally, incentive engineering, designing incentives for all the actors in those systems. And I don't think there's one size fits all solution to the governance and regulation of AI, just because, as you can see, these human AI partnerships can be of so many different types, involve so many complex relationships between humans and machines. So I think it needs to be looked at on a case-by-case basis, and hopefully we can generalize at a sector-by-sector basis. Just to conclude, and I hope I've left maybe 3 minutes to do this. If you're not familiar with the UKRI Trustworthy Autonomous Systems Program, it is the world's largest program looking at trustworthy AI. It involves over, I think now, 200 researchers, and involves the resilience node, as you're part of. And it's focused really on world-leading best practices for socially beneficial autonomous systems. So not just trustworthy in principle, but trusted in practice by individual society and government, which is why I think the human AI partnership paradigm really helps with defining these notions of trust in all these respects. And we have a very quite broad research focus around the design process, the operation of this system, and the societal acceptance of these systems. And many of the various parts of the network, the nodes, the hub, are all addressing those various questions. And lately, in the last couple of months, we've been refining the research themes of the program. And these are the research themes. So we have autonomous systems research areas, the techniques and mechanisms, the public engagement with autonomous systems, human-machine interaction, responsible innovation processes, and the governance of trustworthy autonomous systems. And the topics under these can be quite broad, as you can see. So hopefully you will find yourself in this. There's a lot of topics in here which reflects the breadth of the program. And we have a number of cross-cutting values across all our projects. So EDI, RRI, trust and trustworthiness, fairness, accountability, trust, transparency, and ethics. So recently, just to conclude, we undertook a landscape mapping study where we looked at how the current network, so we have, as I said, of 130 researchers, we looked at the profile of all these researchers and to see where the gaps were. And what we found is that the network is very strong on some fields, creative arts, mathematical sciences, technology, ICT, but we still have gaps in specific areas like philosophy, like law and legal studies. And this was a bibliometric sort of based research that we undertook, but it sort of reflects where we need to engage as a large multidisciplinary program. We need to bring in experts from different fields to really understand the concerns of their end users or the end applications that need to be looked at from their perspective, and eventually inform policy based on a very broad view across all these disciplines. So the key message here is really to engage more with these underrepresented disciplines across the network. So on that note, I will conclude, and thank you very much for the time you've given me.
Thank you very much for the insightful talk, Gopal. So, yeah, I open the floor for questions. Paola?
Yeah. Yeah, thank you very much for your talk. I think you can manage to see me. So actually, I have comments, questions, let's say, how can I say it? So many of the issues that you discussed are actually about, have been studied since many years by the software engineering community. I mean, it's the issue of embedding machines in the society. No, I mean, everything that you mentioned in terms of acceptance or general requirements, that have to take into account the context in which the machine will be deployed are crucial and have been studied. So from this point of view, I think that there is a lot in common. No, but my question is, okay, does the AI component bring something new in this picture? I agree with the autonomous part, but the AI component itself. And the second question is, many things that you said can be rephrased in terms of interaction. So actually, the crucial point is now we have machines that can interact or interact more at a higher level with humans than before. And now it comes, the question of how do we regulate this interaction? And many of the problems you mentioned is a matter of regulation of interaction, which is not law, it's protocols. So, the disaster example that you had, I mean, even in an organization of human beings, you need protocols. You cannot just put everybody together and say, okay, you go and, rescue people. And there are very strict protocols. So I'm just wondering, I mean, we need, it also may be because I'm a software architect, so I mean, it's interactions and protocols are my job. But it seems to me that this is the key part that we have to look more carefully. Yeah,
that's
okay.
And it's a point that I've seen made to me a number of times, and I've worked as part of many teams involving software engineers and machine learning experts who didn't quite understand the point I was making as well. I think you're right. The autonomy makes a difference, but it is a perception of intelligence also that makes difference. You might have, as we've seen, if you deploy a smart thermostat in a home, we've deployed autonomous smart thermostat, and we told people this thermostat will tell you when to turn on your washing machine, and people started thinking, oh, this thermostat is gonna predict the weather now. This thermostat is super intelligent and knows when I want to do things. It actually was never doing anything like that. And I think pointing back to the other example of the drones crashing because of human failure, in that case, the protocol was very, very clear. It was actually the most precise protocol you could ever define, and still it failed because people had the wrong understanding of what the system was doing. People were influencing each other's behavior in these systems, and they're trying to figure out what this thing is doing there, and they all had different understandings of what he was doing out there, and ended up making the wrong decisions. And it was then more to do with authority relationships around that system. And you take another example of the human, the parent looking after their children going into the autonomous vehicle. What is the protocol there? Can you define a generic protocol for all situations like that? It becomes really, really hard. And it's not just about the interaction with the vehicle there. It's about the relationship you have with the operator of that vehicle as a parent. It's to do with what the children can do in that vehicle, or whether the passengers can do. So some of these issues can be addressed from a software engineering perspective. Some of these issues are to do with designing interactions, but a lot to do with the sort of social relationship we have with the system as a whole, not just the machine or the agent that operates the machine.
But you have assumptions, no? Even when you have in a scholar in a scholar bus, no, I mean whatever it is, there is a driver.
Exactly.
You have assumptions on the drivers.
You trust the system. You trust, for example.
You have a trust assumptions. Maybe it's not well posed, but.
Yeah, and that's exactly the kind of thing we need to explore in these very these systems that are out deployed in the field. We have very little time, so I want to give time to the other question. But thank you for the question. Colin, maybe you was first.
Hi there, thank you. And thank you for the, we were discussing that thermostat and its failures this weekend in our very house. So thank you for that. I've got a couple of questions, but I'll keep it to just one, given the time. I think one of the great appeals of deep learning when it started to emerge was that we could do away with all this pesky people understanding data. And we'd just throw more and more data at it and it would get better and better and better and we wouldn't have to care. So I guess there's a couple of questions there. You mentioned the thing about Netflix. It's clearly not good at spotting the unusual and it just aggregates it in regardless. So you end up with these poor things. And I wondered if you had any thoughts about how we should be going forward on that. What should we be doing about getting the community to realize that more data isn't a substitute for better knowledge?
Yeah, it's an interesting question. And I think that Instagram documentary is also very relevant. I encourage everyone to watch that one because many of these companies are using tons of data to make those suggestions to us to optimize what they show to us against a certain objective function. For them, it's about making lots of money, putting as many ads as possible. And YouTube, for example, defines this as watch time, so keeping you engaged, so you keep watching movies on and on. And it is based on more data about people similar to you, or based on what they know more about you, right? So from other platforms. And they tend to hold that data internally and not explain what they're doing. They tend to do their research internally and not tell us why they're pushing things out to us. I think understanding the purpose behind that those recommended systems, what is their objective function? They're not very clear about that. Would help us understand how they're manipulating or using the data that they have. And secondly, understanding the kind of data that they have. So what biases exist in this data? How clear is it to everyone that it is representative of whatever population we would like to be part of, or beliefs we'd like to have. But then really sort of raises interesting questions around the ethics of using everyone's data to change or guide human behavior. I don't think there's a we've solved that yet. I mean, we're not anywhere close to solving that. However many interpretability or explainability tools you design, that relationship with data, our data is I think a much bigger question and more philosophical question.
Thank you.
Hi, yeah, hope you can hear me. Again, thank you very, very much for the talk. I found that really interesting. I think it covered such a wide encompassing field. So thank you for that. In particular, one of the things that I found very intriguing is, and I think, a lot of people here would agree with me, as you put it here, we need to go from these sort of like reactive sort of measures to a much more preventive sort of attitude. And this kind of reminded me of like a discussion I was a part of a few months back at this workshop, with this idea of deploying AI that can still make mistakes. Is that necessarily a bad idea? Because that is unfortunately, it is a very good way of gathering data and being able to learn from the scenario, the experience, and what the problem actually is. So, and as you were saying later on, of course, one shoe won't fit all, and instead you'll have to take a scenario by scenario, product by product sort of basis. But I guess I'm trying to be succinct with this. I guess my specific question with this sort of idea is, do you think that there are any sort of general sort of, I guess you'd call them reactive problems that can never be moved to a preventive sort of scenario? And do you think that perhaps looking more at industry, with cynical eyes, perhaps this could be exploited to try and get more products out there? Because as you say, it's going to be very fast and loose with this.
Mm-hmm. Yeah. So I try to sort of raise the sort of RRI approach as being a key solution to this. I think anticipating the consequences of technology and anticipating the consequences of the algorithms or systems that we design, and doing so by engaging with the end users right from the start. So when we're designing products and industry, you might be designing an algorithm and you think it's not relevant to society, it's just an algorithm that improves the performance of X, right? But improves the performance of X in what circumstances? And then you need to think, okay, facial recognition technologies, recognizing faces was never designed for predictive policing. When we designed the algorithm, we wanted to detect eyes and noses and mouths, but then it was taken by industry, and industry just ran with it and said, okay, someone needs a product, we think this is the right product to build, not thinking about the wider consequences of this. And that's because they didn't engage with the right researchers or disciplines to think about the ethical issues, to think about the legal issues associated with them. And I think that's where we have an opportunity within the TASK program to change that thinking, the way industry works with the research community, to decide on how they shape their products and to be more proactive in designing them so that they don't hurt society, they don't hurt individuals. And similarly, we need to be working with policymakers to inform them of the potential uses of these technologies before they end up designing irrelevant policies, for example. So I think there's an opportunity here. We should not be doing what we were doing before and keep the same mindset. We have an opportunity to change with the thinking in industry and in government when it comes to building and deploying these technologies. We need to work harder on that. I think we've been too focused on the engineering elements, and we need to go out a bit more now and think more broadly about the impact of what we do.
Thank you. So, Tim, would you like to read your question from the chat?
No, thanks, Roderick. Can you hear me?
Yes, we can.
Yeah. No, that's a really fascinating talk, Gopal, and obviously I've sort of put a couple of paragraphs down there. One of the aspects that it sort of seems to me is that AI in itself is really only another algorithm, and as such, but it's not just another algorithm. AI brings its own characteristics, and one of which is this non or time varying response. But an awful lot of the rest of what we actually start talking about is common with other algorithms. Like the MCAS system on the Boeing 737 didn't use AI, but it still failed to deliver the intended result when used in anger in the field. And a lot of times I tend to think things like that, like one of the watchkeepers, for example, my understanding was it had two of the pitot tubes ice up at the same time, which had never actually been thought of as a likely scenario in the development. So therefore hadn't been included in the processes, hadn't been included in the design. And likewise, one can debate what was actually how the decisions were made at Boeing, but MCAS ended up in the field. It strikes me that an awful lot of what is being discussed here is really how do you test systems with different degrees of safety criticalness prior to delivering them into the field. for things like health systems as opposed, and the heating system clearly hasn't been tested in that scenario. It's or at least it doesn't appear to have been. It's just been ignored and it's been put out into the marketplace by a beware sort of thing. And I think you've raised all these issues. I think it's really important. But the thought that comes back to me is, in terms of addressing AI as such, how shall I put it, autonomous. AI is not in itself a requirement of an autonomous system. It's algorithms which are a part of an autonomous system. And so there are many other aspects to what you have to do with those systems to get them out there. And as a number of people have alluded today, the propensity of data, the increasing number of systems, the speed at which these things compute these days make it much harder to analyze the test results. It's not 50 points as it used to be, it's thousands or millions or billions. And, I just wonder if I'm saying the same thing as you there, or whether I'm saying anything different, or whether you disagree with me.
I completely agree with you. I think we had this debate within the community about how do we define autonomous systems, and in the end we came up with a very broad definition that included humans in the loop. Not just AI-based systems, but also algorithms, automated decision-making systems. So it's a very broad definition, because I do think as soon as these systems become a bit opaque to the end users, like in the MCAS system, and the whole movie is done about the MCAS system failure, right? And the whole other issues around testing that system effectively out in the field, and the fact that maybe the pilot and the assistants were not trained or didn't encounter these situations very often. You have all these other issues beyond just the algorithm works in this setting, right? So this sort of pure formal sort of way of testing this system. It's the skills issues, the training issues, the long sort of lived nature of these interactions. So you're interacting with the system over long periods of time. Can you really test this system in hundreds of situations that really reflect real world conditions? Very hard to do that, which is why you need to sort of anticipate these problems ahead of time and think of system not purely from an algorithmic perspective, but thinking about how humans will appropriate them, how they will be used, or the technology will be used by different industries. You might have designed an algorithm, but it's taken out of this sector and then deployed in another sector. So before it's done there, have we actually verified that it is going to result in the intended outcomes? I think we are very reactive. I think that's where, as the systems are becoming more and more complex, being able to pull data from multiple sources, massage data from huge databases in real time, we're starting to realize that us humans are not skilled enough to deal with that. We're starting to realize we're not getting the right training to deal with that, and that's why we keep reacting. And I think we could have anticipated this. I mean, we should now be anticipating these issues, and it's not just about how sophisticated the AI is the idea of having just complex automated decision making in a number of systems that we need to react to when they fail, or will make decisions on our behalf, or will influence our decision making. I think we need to think about all these issues as part of a partnership between us and the machine, not just this machine will do X, so how do we make sure it always works the way we want it to do. So tons of issues here which we're trying to address across a broad range of projects, which is a really exciting time, but it is, I think, a unique opportunity, and I think I encourage all of you to join us in trying to solve some of these issues.
Yeah, no, I'd love to carry that conversation on with you. I'll throw one more little comment in on the MCAS. One aspect of it, which I think tends to get forgotten, is that the high-speed aspect of MCAS was what it was originally intended for, and that worked as intended. The need to apply it at slow speed was only discovered fairly early on in the flight testing. But when you say fairly early on in the flight testing, the pressures on finalizing stall speeds put tremendous pressure on the development of a solution and finalizing it rapidly. So I suspect there were some very unusual time pressures on the development of that adjustment to that system, which obviously would have had implications. And then, of course, you get into all the legal side of, well, what did people behave as they should have done, and so on and so forth, and did they test it adequately, and were the assumptions adequate, and all the rest of it. And you can debate that for a very long time. But yeah, having been involved in certification programs and the way, and looking at the way they're fairly compressed, that must have been a difficult set of decisions for Boeing to make, I think.
Well, I think the big worry I have is that we are increasingly seeing, AI-based systems of highly complex decision-making systems in our phone apps, in our cars, etc. But this and in consumer apps. But what is the certification process for these simple things that we think will not have a huge impact on the world, but for example, guide our vehicles? The Waze app, for example, that can easily be hacked by taking a bunch of phones in a car, and that will completely throw off Waze and create a traffic jam on Google Maps, right? So things like that, simple consumer apps that will clearly change the world. So we need to think about, the certification process very, very carefully. Definitely.
Absolutely agree.
Have another conversation about that.
No, thanks, Gopal.
And then one more thing I'd like to pick up on, Radu, I had this question from Robin Williams.
Yes, I think Robin is prepared to make this comment and ask the question, and we have time for this one more question.
Yeah, I was taken back to some work we did on the dependability of computing interdisciplinary research collaboration with Stuart Anderson and Cliff Jones about 10 years ago, where we showed that the formal methods people had built their kind of failure trees, but when you looked at actual disasters and collapses, the failing was never in one of the ways anticipated on those trees. So things will always fail in different ways to anticipate, and that made me want to be a bit cautious about your role about upfront co-design and human AI interaction design, which I think is a good idea, but I would be very worried about relying on them. And we've been doing some work, particularly looking at this question of testing and certification, and come down strongly in the favour of post-market surveillance at scale, as no less important, perhaps as significantly more important, but also to address the. Of course, you've got you characterise the complexity of the situation, but there may be ways that we could begin to manage that complexity better. Yeah, and what interests me is a friend of mine has a Tesla car, and she said that last week Tesla upgraded the operating system so she could no longer work out what button did which. Yeah, and actually we know it was when were those guys doing that work in the States, in California? It was the 1960s, wasn't it, when they invented the WIMP interface and decided you need to stabilize the icons and the meanings of things. So suddenly Tesla had radically transformed what the command structures. So earlier learned routines were no longer systematically applicable. So I think we need to find ways of building modes of interaction, predictable modes of interaction that become widely understood as humans engage with AIs. But even that will not prevent problems from emergent behavior. So we also need to do downstream as well as upstream design of these as kind of programmatic features. Just a question.
Yeah, I think the point about engaging with users, and when I talk about users, I'm not just talking about people who interact with those systems. It's also industry, it's also related. I think of it as being impacted by the technology or have a say about how the technology is deployed. So that's one thing. In terms of iterative design, you're right. You build a system, you think you've identified all the potential failures in the system, but something else comes up and it doesn't work. That's I think those chance events are always going to be there. It's just that there is a tendency to ignore the sort of organizational structures or the social relationship between humans and machines in the design of these machines. I think that's what I was getting at. But yeah, I don't have a solution yet for designing for complete perfection. But I think often we miss that element, and that as I mentioned earlier, this relationship with an automated decision-making system that is influencing our behaviors, our beliefs about how the system works, and ultimately our decisions. So I think it's not going to get much worse in the future if we don't do that. I think if we don't not just engage with users, but think about the broader impact of autonomous systems technologies on human decision making and beliefs.
Right. Thank you again, Gopal, for the thought-provoking seminar and answers. I'm afraid we need to stop here, but there will be future events organized by the task program where this discussion can and needs to continue. So thank you also to everyone who attended, asked questions, and participated in the discussion. And I'm looking forward to seeing you again at our next seminar in 2 weeks' time. Goodbye now.
Thank you, Adi.
Thank you.
Thanks for all the questions. Bye.